Hello everyone, I'm Li Yunze from National Cheng Kung University. Today I'm going to give a presentation on a recent work KV. This is a joint work with my colleague Ke Zhongmin and my advisor Zhang Dawei. In-memory key value cache systems or KV stores are now widely used in many web applications. KV stores use high-speed memory devices as caches of the database to reduce the overall request latency. There are motivations to use emerging non-volatile memory on KV stores. These memory devices are byte addressable and have comparable performance to traditional DRAMs. In our paper, we target phase change memory PCM. PCM is a resistance-based memory which represents and stores data by resistance. The data retention time of PCM is limited by resistance drift phenomenon, which means that the resistance of PCM cells increase with time even at room temperature. Once it exceeds a threshold, the data is no longer available. The PCM cell is written by programming its resistance into a range called target band. As we desire a longer retention time, the target band gets narrower as well. In such case, the write latency also increases since multiple write iterations are required to accurately program the resistance into the target band. However, it has been shown in the previous research that we can speed up the write at the cost of retention time. The table shows the iterative write model from the research paper NVN Do It. And we can actually see the trade-off between the retention time and the write speed up. In our paper, we call the first row a slow write and the last row a fast write. Since NVN-based KV stores were proposed, one of the main challenges has been the performance impact due to NVN's longer write latency. A common strategy proposed to alleviate the problem is to reduce the overall write count. In our paper, we do not focus on reducing the write counts but on speeding up the hot data write. Specifically, we are motivated by the so-called Hotspot issue, which means that there's actually only a small proportion of data is accessed frequently in many real-life workloads. In our opinion, it is redundant to write hot data with long retention time since they tend to be updated again very soon. In other words, it is practical to apply fast write on hot data. Based on the insight, we introduced KV. It dynamically captures hot data in applications and uses the fast write to speed up the write operations. Our work achieves 43% and 83% throughput improvement on the single-threaded and multi-threaded YCSB workloads respectively. Our work is highly portable and does not require significant software refactoring on existing KV stores. For instance, we made about only 13 levels code modifications to integrate our work into Memcached, which has been a popular KV store in recent years. Now let's move on to the implementation section. Here I show the model of KV. It includes 4 modules, which are the KV interface, the hot item predictor, the log structure allocator, and the reclamation eviction manager. The hot item predictor is responsible for calculating hotness of items and determining their write modes. The hotness of an item is quantized as its write frequency. When an update command is received, the hot item predictor determines its write mode by comparing its write frequency with a threshold. The threshold is configured to 1 write per 100 of seconds in our work. Now let me introduce how KV manage the NVN device by introducing the log structure allocator and the reclamation eviction manager. Let's start with the log structure allocator. The NVN device is divided into a fast write region and a slow write region. The fast write region is 64 MB by default and is independently managed by our proposed log structure allocator. We are doing so because we have found it inefficient to use the original Slab allocator for the fast write region management. To explain the reason, I will first illustrate how the original Memcached Slab allocator works. The allocator organizes the memory space into 1 MB Slab pages, and each page belongs to one of the predefined Slab classes. The pages are cut into chunks, where a chunk is an allocation unit for an item. When an item arrives, the allocator will choose the best fitting chunk for the allocation. However, there's some problem when using this mechanism on the fast write region. Since most of the hot items are small items, and when some pages of big chunks are allocated, their utility usually becomes really low. According to the policy of this allocator, those chunks can neither be allocated to the small items nor be reclaimed. We introduced the log structure allocator to address the problem. The allocator organizes the fast write region into linked 1 MB segments. Items are written in an appending fashion within the segment. When the segment is full, the allocation moves on to the next segment. Next, let me introduce the Reclamation Eviction Manager. This module has two responsibilities: reclaiming free spaces from the fast write region, as well as evicting out-of-date data from the fast write region. The reclamation process happens when the number of free segments falls below a threshold. When the reclamation thread is scheduled to run, it will choose the oldest segment and drop the live items in the segment directly if there's any. We currently use the approach for its easy implementation, but it may yield hit rate penalty. However, since the oldest segment tends to contain the fewest live items and the fast write region size is well tuned based on our evaluation, we actually calculated a negligible hit rate penalty. Next, let me introduce the Age Item Eviction. The items in the fast write region have limited lifetime, which is 100 seconds as mentioned before. It is crucial to evict these items before they become invalid. This is done by the eviction thread. The eviction thread is scheduled to run every 10 seconds. Once scheduled, it will scan through the fast write region and check the lifetime of each item. If an item is going to become invalid in 10 seconds, then it's going to be evicted in this iteration. Otherwise, it will be left in the segment. We currently configure the eviction period to 10 seconds to balance the computational overhead and the hit rate penalty. Finally, we come to the DoorKV interface. The DoorKV APIs can be used by the system designers to easily manage the fast write region. Here I show the hardware environment of DoorKV. Thanks to the door retention MVN interface contributed by the research paper MVN Do It, it is practical to build DoorKV on top of it. A supercapacitor is required to flush the data in the fast write region back upon the power failure. Supercapacitors are not uncommon. In fact, they are used in existing NVDIMMs product to flush the data in DRAMs back to the NAND flash chips when the power failure occurs. Now let's dive into the evaluation section. The table shows our evaluation setup, and as mentioned before, we use the door retention model from the research paper MVN Do It. We have modeled different YCSB workloads with various of operation ratios and value size ranges. each workload executes 10 million operations on 10 million of items. And items selected for operations are mostly small items. First of all, JOKV improves the overall throughput in write-heavy workloads. For workloads with big items, the use of fast write reduces the queuing delays of other operations and result in significant throughput improvement. As JOKV targets at ambient write, it adds a little computational overhead in the read-only workload. Here I show the operation ratios of all the conducted workloads. It shows that JOKV works because that most of the original write operations can actually be replaced with fast writes. In a highly skewed workload, the throughput improvements is even higher since JOKV is able to capture more fast writes. To evaluate the scalability of JOKV, we scale the number of YCS client threads up to 16 based on workload A3. The result shows that we achieve 83% of throughput improvements. Finally, I would like to explain how we tune our fast write region size. It is a trade-off between the hit rate and the hardware cost. As shown in the chart, a 64 MB fast write region is sufficient to reduce the hit rate penalty into a negligible result. And that's all for today. Thank you so much for your attention. Please feel free to ask questions.